Okay, so we're talking about lesson 3.2 on Monday, Tuesday, Wednesday. So 3 days to talk about this one. So if you're not in class on Monday, Wednesday, you can ask me questions on Tuesday. This assignment will be due by the beginning of class on Thursday. So if you're only here on Tuesday and Thursday, if you want to ask me an extra question in class on Thursday, that is okay. But hopefully everybody can get it done in those 3 days. So here's the main deal in section 3.2. So mean value theorem is the only theorem that I'm going to cover in this section. This section is actually titled Rolle's theorem and mean value theorem. Rolle's theorem is only a Calc BC topic. So we do not have to cover that for Ivy Tech or for the AP exam. So we're going to stick with just mean value theorem. And remember, mean means an average. So we are literally talking about the average rate of change in this case. So they have a really good illustration in the book about this theorem. So let me talk about what it says. It says, if f is continuous on the closed interval, they call it AB, and differentiable on the open interval AB. So they're saying it has to be continuous, including those endpoints. It has to be continuous all the way through. It also has to be differentiable, but if it's not differentiable at the endpoints, that's okay. Then there exists a number somewhere in the middle. So somewhere in this interval, there's some number where the derivative is the average rate of change. So let me show you in the illustration because I think that makes a lot more sense when we talk about it. Let me see if I can get the book to where you can actually see it here. Okay, so this right here is talking about this theorem. So it says if I have this point A and point B, the average rate of change of those 2 points is the secant line. So the slope of the secant line gives me the average rate of change. They are saying that the slope of the tangent line at some point in that interval will match that. So these will be parallel to one another. And that is true for anything that is differentiable from A to B and anything that is continuous from A to B, including those endpoints. Okay, so let's see what this actually looks like in practice. So the first example they gave us was example 3. Again, because examples 1 and 2 cover Rolle's theorem, which does not apply to us. So example 3 says, for this function, f of x equals 5 minus 4 over x, find all of the values of c in the open interval 1 to 4, such that this is true. Well, this right here is mean value theorem. The mean value theorem told us that that is true. So we need to just find all the values for that work. So the idea is we have been finding the derivative a lot and setting it equal to 0. Now we are finding the derivative and then setting the derivative equal to whatever this average rate of change is. So in this case, I can find this actually pretty easily. So I'm just going to right here in the problem say, okay, well, that equals f of 4. So if I go back to my function and I plug in a 4 right here, this would be 4 divided by 4, which is 1, and 5 minus 1 is 4. And then minus, plug 1 into your function. So I'm up here, take 4 divided by 1, I get 4. 5 minus 4 is 1, all over 4 minus 1. Because that's my interval, 1 to 4. All right, so that gives me 3 over 3, or just 1. So they're telling me that at some point C within this interval, my derivative should equal 1, and they want to know where that's happening. So I'm going to find the derivative of this and then set it equal to 1 and find those values. So the derivative of this, so f prime of x, let's first rewrite this. This is really 5 minus 4x to the negative first. That's how I would rewrite it. It's getting kind of blurry. Let me take the book out from underneath here. There we go. That's a little bit better. Okay, so this is my function. So now I'm going to do the derivative. Well, the derivative of 5 is 0, so I don't have to write that down. I'm going to bring down my negative 1. That makes this a positive 4. and then x to the, I'm going to minus 1 from this. -1 minus 1 is -2. So really my derivative is 4 over x squared. Okay, so I want to know, when does 4 over x squared equal 1? When is it equal to this average rate of change? So I'm going to multiply both sides by x squared. That gives me 4 equals x squared, and then square root both sides. That would give me a plus or minus 2. Don't forget that it could be -2, right? So either +2 or -2. So now I just need to look back and make sure that these values are in my interval. So if I'm talking about the interval from 1 to 4, -2 is actually not in that interval. So the only value that I need to think about is 2. So this C value that they were talking about that was within this interval 1 to 4 is 2 in this case. That's where my slope of my secant line and the slope of my tangent line are both 1 at that point. Okay, now where you see this put into application a lot, and this is a very real world situation. They use this a lot in actually in court cases that involve traffic issues, and sometimes you'll see they have cameras set up at stoplights and things like that that will clock your speed, and they can find whether or not you're actually speeding within a certain interval. So this particular problem says 2 stationary patrol cars equipped with radar are 5 miles apart on the highway, as shown in this figure. So here's a patrol car, here's a patrol car. As a truck passes the first patrol car, as he goes past right here, that patrol car clocks him at a speed of 55 miles per hour. 4 minutes later, when the truck passes the second patrol car, he's clocked at 50 miles per hour. So he was going 55 here, he was going 50 here. But that was only 4 minutes away, and it's 5 miles away. So we're supposed to prove that the truck must have exceeded the speed limit, which was 55 miles per hour, at some time during that 4-minute period. Now, how often would any of this happen? How often would you have patrol cars that far apart, and so on and so forth? So this doesn't happen very often, but it probably would happen if you had kind of preset cameras that would clock their time, their speed, I'm sorry. So that's probably when it would happen the most. Okay, so I'm going to talk about this in this particular situation. I'm going to talk about it using mean value theorem. So the two things that I need, so if you think back to this, I need an f of b and an f of a and a b and an s. That's not c, I'm sorry. This should be an a. Sorry, guys. Correct that on your paper. That should be b minus a. So I need those values. So I need to think about what is it that I'm talking about. So in this particular problem, I'm talking about as time goes by, what is this truck's position? So T is going to be my time, and I'm going to use hours for that. Time is in hours. And why would I use hours? Because we're talking about miles per hour. They've already given me the miles per hour. So I don't want to have to convert to another time. I don't want to put it in minutes because I'd have to convert my speed to minutes. So I'm going to leave it in miles per hour. And then this is going to be my position. So how far it had traveled, okay? So I'm going to have a starting time and I'm going to have a starting position. That's going to be where that first patrol car was. So I'm going to say that at when t was 0, when no time had went by, the position was 0. The other piece of information they gave me, though, was after 4 minutes, after 4 minutes, they told me the position of the truck. So let's talk about that for a second. I don't really need that book. I think you guys could see it in your book. So after 4 minutes, the position of the truck was 5 miles away. All right, so let's talk about this then. So 4 minutes, that's the wrong unit. I need this in hours. So this really means 4 over 60 because it's 4 minutes, 60 minutes in an hour, right? So really this is 1/15 of an hour. That's pretty important. So what is my S of t at that point? So this is really, I really should say this is S of 0, right? And this one would be S of 4, my position. S of 4 was 5 miles away. He was 5 miles away, and I could say miles here. Okay, so I'm going to write out my position function then. So I've got my f prime of c, I'll just call it that for now, would be my s of t minus another s of t. So my s of, I'm going to use s of 4 minus s of 0 all over 4 minus 0. I'm going to write it out like that. Well, s of 4 was 5. S of 0 was 0. And then my time, which I should not say 4. This was not 4. This was 1/15. I'm sorry, guys. I still put it in minutes. So this is 1/15. So this is 1/15 minus 0. Okay, so this is 5 over 1/15. Okay, so if I solve that out, 5 divided by 1/15, that's the same thing as 5 times 15 over 1, which is 75. So according to this, that truck at some point was traveling 75 miles per hour. Now, I could figure out exactly where that was happening in my position as long as he was going, if he was increasing and decreasing at the same rate all the way through, then I could plug that back in and tell them at what time that happened. That is obviously a very varied situation when you're talking about driving down the road, because he could have sped up to 80 at one point and then he could have slowed back down to 60 and so on. So we know that at some point though he was going an average of 75 miles per hour. So that would mean, yeah, he definitely exceeded the speed limit by 20 miles per hour. Okay, so there's a start for this lesson. This is the only video for this lesson, but we can talk about those problems in class. So I'll post the homework assignment with this video and just talk to me in class about which ones you need me to go through.